Our next speaker from Poolside, and this is an interesting, this transition from artisanal to industrial. I think we're all a bit worried about that. As software developers, we think of ourselves, many of us think of ourselves as craftspeople, moving to a more industrial world. So I'm certainly looking forward to hearing a bit more about this. And I'd like to introduce from Poolside, Joe Rowell.
First of all, I'd like to start by saying thank you all for having me. This is a great pleasure. And I want to sort of frame the talk that I'm going to give a little bit. So James earlier mentioned that this session is about talking about the foundations behind the applications that we heard so much about yesterday. This talk is about the foundations behind the foundations. So what I'm going to talk to you all about is how we build models at Poolside. So the entire process from taking a data set, the whole way through to the end of actually getting a model that we can use for things. You've all heard of us, of course, because we're one of the sponsors, but I just want to give you more context on who Poolside is. So we're a company that's pursuing AGI via the medium of software development. So what that means is that we write models, or we build models, that are designed to be good at coding tasks, essentially. From as simple as generating unit tests or things like that, through to essentially end-to-end application development. That's really what we do. And it's a good thing that James pointed out the title, actually, because I think something that's become very clear over the last year is that AI is really undergoing an industrialization period. I think everything in this room, every commodity, every chair, every item of clothing, is the result of some industrial process. It would be impossible to detail all of the things that have been made in this room. And really, as someone who works in the space, I don't know if you find the same thing, but it's impossible to keep up with the number of models that are coming out every day. There's new models that are released every week, there's new things that continue to come out, and it's a real frenzy of new ideas. Is everything?
How much of that did you get? Do you want me to start again from the beginning, or? Okay, great. So today I want to talk a little bit about how we build models industrially speaking. So how we go from an idea, something that we want to build, something we want to develop, into something that we can actually use. And to start, I really want to begin with this very traditional way of building models. So this is what I would call the artisanal way of building models. You start with some data set, perhaps you got it from the internet, perhaps you got it from your friend down the pub, it's kind of irrelevant. Then you choose some architecture, and choosing here is in air quotes because normally it's just based on your vibes, right? You think to yourself, oh, this is a reasonable way of doing this, but you don't have any way of knowing. You then just train the model, and by the way, the word just there does a huge amount of heavy lifting, right? Anyone who's actually trained a model will tell you that this block in the middle here can take months and years to actually get right. And then once you've got some model that you've trained, it's got some knowledge of the world, you do this thing at the end called fine-tuning, where you take it and you teach it to do some particular task. I think every model that we've seen so far at this conference, I might be wrong, has been a fine-tuned variant of some existing model in the world. So it's been some model that has been pre-trained somewhere and people have come along and done some like LoRa adaptation or things like that. So this is the very traditional way of training a model. But the thing is that this is just one out of the universe of models that we could have trained. If you take any of these pieces and you change them even a little bit, the model that you get will be very different. It will have different properties. In fact, those of you who are into sort of bespoke clothing or things like that will know that every piece is individual because it's tailored for you. That doesn't mean that it's good, it just means that it's tailored for a particular task. And one of the things that you really lack here is any ability to get insights into what's actually going on, right? We just know that we have trained a model, but we don't know whether we've trained a decent model. So if we were to try and make this process, say, more reproducible, the first thing we would do is we would add a way to evaluate the model that we've trained, both during training and at the end of training. Now, I want to be clear, this is not a silver bullet. You will get people all the time who will talk to you about how evaluations are really all you need. But actually, I think anyone who's used a frontier model will tell you that that is not true. The important thing behind a model most of the time is how it feels when you interact with them. right? How they converse with you, the nuances of what they do and don't know. It's very hard to actually capture that in an automated way. And so I want to be clear here, I'm not saying that this is some silver bullet. Instead, what I want to point out is that this is kind of like the standardized testing that you undergo at school, right? It's to make sure that the model is reaching some developmental milestones as you're training it, so that you can intervene if you need to, or you can adapt if you need to, right? This is not some overarching thing of, oh yeah, this model is amazing. It's just to make sure that as you're training the model, it's doing things that are reasonable. Of course, to run evaluations, you need to actually be able to run the model. And so the next piece that you need when you're building a model in some sort of reproducible or industrial way is you need a way to run inference. And you need this remarkably early. In fact, we tend to run, I think we start running our evaluations a few thousand steps into training, so you can't delay this process. You need it remarkably early. And one of the things about this that's really important is that you obviously need to offload the weights of your model as you're doing the training. But you don't want to slow your training down. You don't want to stop your training because it's incredibly expensive. It's incredibly difficult to do this. So you also need to build some way of quickly transferring weights from your training to your inference. And by the way, it's only a single line, but this is one of the hardest things to get right. Because actually, more often than not, these two things are entirely independent. You don't want this inference service to always be running. You only want it to run when you're running evaluations or when you're doing something else. Whereas by contrast, your training is presumably running all of the time. And equally, you want the ability to scale these two things up and down independently, right? You want the ability to scale the number of nodes that you're using for training, yes. And you also want the ability to scale the number of nodes that you're using for inference. And you don't want them to be tied together. So even at this stage, we've already got a huge amount of complexity going on. So I mentioned earlier, we train models for code execution, right? That is our main thing. We want to help people to write better software. Once you have this bit at the top, so you have all of this infrastructure around evaluating your models and stuff like that, you can do this stuff at the bottom. So you can add things in that will actually make your model better at particular tasks. So just to give you an example here, I think one of the things that really morally bothers me about LLMs is that to get them to be good at things, you need to show them the entirety of what humanity has essentially produced in that field. And it's nonsensical, right? On its face, it's a farce. Because if you had to read every single C++ program that ever been written to learn how to write C++, you would never get started. It's nonsense. Instead, the way that humans learn things is by doing them, right? It's by actually sitting down, it's writing code, it's getting compiler errors, it's learning from that experience of doing. And so one of the things that we do during training is we allow a model to execute code. There's a whole load of things that goes into this, right? You have to take your repositories and containerize them, you have to define tasks properly, you have to define some clear success and failure metrics. So this is not necessarily a straightforward thing to do, but when you have it, your models get way better than they were before. And actually what's really interesting about this is that you can place this at any point during your training. If you want to, you can just do it during pre-training when the model is already learning from next tokens, or you can do it right at the end when you're doing fine-tuning, or a mixture of any of them. You always have those options. You always have the ability to take these pieces and just put them in slightly different places. I think something that should be obvious, one more thing that's very important before we get on to the next point is I mentioned earlier that we had just picked some architecture in some way. But this is not really how science works, right? If you wrote a paper and you said, I'm just going to randomly choose something, and you had no explanation as to why other than the vibes seemed good, that's not how you do anything in a rigorous way. And so there's this very popular thing in the industry at the moment called ablations, where you take some architecture or you take some choice, you train a small model in some way, and you see, okay, which one is better? Which one works better on this data that I have? Which one works better in this setting? The thing is that coordinating all of that by hand is really, really tough. There's a lot of stuff that you just need to do to even get off the ground, right? If you had to sit and babysit all of your training runs that were going on in parallel, it would require a much larger team and a team of people who, quite frankly, are doing work that isn't that interesting or important. So what we did was we built this thing called our model ablation platform that lets you, when you're training a model, say, hey, I want to vary these parameters. Please go off and do all of the work for me. And this, I have to say, from all of the things that I'm going to talk about today, has been the most transformative thing about how we work internally. If I have an idea that I want to try, I implement it, I start it on a weekend, and by the time I come back on Monday, it's all done and I can look at it. Or overnight, or over lunch, whatever it is, you just define what it is that you want to do in a for loop, essentially, and then right at the end, voila, you can see which one is better, what worked, what didn't, all of this. And it makes having confidence in the models that you actually build really easy, right? Suddenly you have a much better way of understanding, okay, of my solution space, of all the models I could train, this one is going to be good. And it just makes your life so much easier. As I've kind of already mentioned, there's a lot of pieces that are in movement here. And I really want to emphasize this point because I think as an industry, we really suck about talking about what actually goes behind model building. A great deal of modern model building is essentially systems work. And I want to be clear what I mean by that, because it's an overloaded term. On the one hand, you have to coordinate all of these pieces, right? If you look at this slide, just scheduling all of these jobs, making sure that they all run when they're supposed to, making sure that nodes don't fall over, making sure that all of the infrastructure works, is already a huge engineering challenge. On the flip side, there's also a lot of low-level optimization work that goes into making all of this run efficiently. So recently, Poolside announced that sometime next year, we're going to have something like 50,000 GPUs. A 1% saving there is 500 GPUs, which is a huge unit of work, right? You can actually do useful and interesting things with that number of GPUs. And so even just doing like the traditional systems programming of taking some kernel and making it 1% faster actually has a real and beneficial economic impact on your company. Although a lot of it is systems work, I want to make it very abundantly clear, the rest of it is science, right? It's this process of having a hypothesis, testing a hypothesis, smoothing out all of the variables, recording what it is that you've done, and making sure that you can repeat your experiments in a way that actually makes sense. One of the problems that we had very early on was that you would do a training run once and it would give you a model, and then you would do it again and it would give you a model that was ever so slightly different. And it makes your life just completely infuriating because was it because I introduced a bug? Was it because training is non-deterministic? Was it because I woke up on the wrong side of bed, right? You have no idea what that difference is. And so building a way to enable you to actually do this sort of science, this real rigorous experimentation, makes your life so much better. It's really how you have to work if you want to produce models at scale. One of the things that really contributes to that in a big way is your data. Now, this diagram is deliberately simplified, but this box here does so much heavy lifting, it's not even funny. I've put it down as filtering and lineage, but in practice, you could have any number of about 30 different steps, various mixes, parameterizations, different data sources, things you're going to include, things you're going to exclude, different thresholds for different parameter sets. It's a real pain to do this. And if you were to do it by hand, you would go insane. You would make a mistake. You would leave something out. You really need to lean on the power of automation here to actually get this to work. So inside our model factory, what we have is a way of essentially uniquely identifying each data set and the transformations that were applied to it, and the ability to replay those filtering steps and tweaks that we made to each data set on demand. You just go in, you click a button, and it does it all over again. It rematerializes all of your changes. And actually something we'll see later on is you have a huge top-down view of all of the data sets that went into a particular model at any given point. You can recreate all of them. You can go from the beginning if you want to. Everything is just completely deterministic. And it just makes your life so much better. You don't have to worry about so many of the low-hanging fruits or the the little specks or details that would otherwise trip you up. Now, in some things, these details are desirable. Right? I've already spoken about clothing. In clothing, the individual maker's marks or those details is really desirable. But in large-scale manufacturing, you don't want that. You want to have this process where everything is going to be exactly as you expect it to be. And having this filtering and lineage really helps with that. Now, of course, there's more to this. One of the secrets of modern AI is that we all use the internet. Right? Everyone takes all the data on the internet and trains on it. That's not a surprise. The thing that we're less good at talking about is that actually we spend a great deal of compute as an industry on rephrasing data, on taking data and putting it into new formats that are actually more suitable for our model. So one of the big things over the last year, for example, has been agentic workflows and conversations. There are actually ways that you can phrase your data early, so like way before you do pre-training, that actually give you better agentic models at the end. And so you can use a great deal of compute to actually take this and to rewrite your data in a way that is better for your model. And equally, of course, you can just generate data synthetically, right? You can query some model, you can get some response. Perhaps you've got some data that you really want to train on that's underrepresented. Well, you can use synthetic data generation for that. And of course, that also relies on inference, right? That relies on the ability to query a model, to ask a model questions, to have a conversation, basically, and to get some answer out. And something I really want to point about this here is that you can see all of these boxes are beginning to talk to each other in quite a big way. In reality, I would say that every box on this diagram talks to every other box. It's a fully connected graph. None of these really sit where they sit for the sake of this conversation, but the point about this is that the power of your good abstractions can't be understated in this world. Good abstractions compound, especially when you're building models. And in this context in particular, once you have these pieces, there's so much more that you can do. By the way, another box that's here that I really want to emphasize is in a traditional way of doing model training, you decide on your data set ahead of time. You pre-install it manually on the nodes that you're going to use for training, and then that's it. It turns out that this is actually kind of a dumb thing to do for a couple of reasons. So one, it means that you've got to predetermine your data mix ahead of time, which is already kind of difficult in some senses. The second thing is you have to know which nodes you're going to train on, which again is actually a real pain, right? GPUs aren't actually that reliable. Sometimes you've got some other pressing compute need in the company. You need to scale things up and down. It's not easy to just decide ahead of time what it is you're going to do. And the last point that I really want to point out is that sometimes your data is so expensive to actually generate that you want to start training before you finish generating it. So annotations are a good example. Anything where you have a model that's somehow judging the quality of your data, you want to be able to start doing all of this stuff before this stuff on the left is even finished. And it turns out that one really nice way to do this is actually to build something that enables you to stream your data to the nodes that are doing training. Now again, this is only a small box, and I want to make it clear, this is not trivial, right? This is a very difficult thing to get right. But when you get it right, it enables you to do so many great things, right? Suddenly you can play with your data mixes on the fly. Suddenly experimentation becomes very easy because you can say, hey, I did this training run with this, 50% of this data set and 50% of this data set. What happens if I do 70-30? What happens if I add another one in? What happens if I tweak how I do learning rates for different things? You can do all of these things just by decoupling your previous assumptions that you had about how training should work. Of course, I mentioned earlier, it's right behind me. I mentioned earlier that evals are not everything, right? You want to be able to do some sort of manual checking of things. And so we have this platform internally that lets you just test a model, right? You take a model, it's automatically deployed, all of this stuff works, and you can just interact with it. And by the way, I know the way that we normally talk about this industrially is, you just do chat or something, right? You just do an agentic query or whatever. It turns out that this step at the end is really useful for doing very small sample inspection. So to give you an example, let's imagine that you have a model that is really, really good at JavaScript, but for some reason sucks at TypeScript. I can't imagine there's many models that do that, but if you were to find one, it can be very useful to look at what the model does on a particular sample. So you just drop a TypeScript sample somewhere, and you see what the output is. And it sounds crazy, but if you just look at the data, after a while you get a good insight of, oh, actually, this fundamental thing is what my model struggles with. This is where it's getting muddled up. This is where it's getting confused. How can I write an eval for that? How can I make sure that when I train a model next time, that this is properly reflected in my data set, and so on. And it really makes having a sort of a good idea of where your model sucks much easier. It makes it much easier for you to look at it and go, okay, this is where I'm going to make things better next time. Of course, I've already kind of hinted at this, but you don't just want to do these ablations on just your architecture, right? You want to adjust all the things. You want to change all the things. You want to be able to play with your data mixes. You want to be able to play with how the data is blended, all of these things. Again, this diagram is not as representative as it should be. Really, arrows should come from here to all of the boxes on this diagram, perhaps with the exception of valuations, because you want to be able to play with everything. You want to be able to adjust every knob that you can to get a model that is as good as it can possibly be. And by the way, something that really should be from here is we've started doing a thing where we will, before we train a model, we will just see, hey, what is its inference characteristics like? When we actually deploy this, outside of it, just being a small model or whatever, what does it look like to run this model in production on certain workloads? And actually, when your models are roughly the same, when they perform roughly similarly, this is precisely how you should decide what it is that you're going to do. Right? You should look at how it's actually going to be when you deploy it in practice and what the performance characteristics of that look like. I want to really end on this point, which is all of the boxes in the previous diagram were kind of arbitrary. There's a reason why they're there, yes, and I hope I've done a good job of explaining them. But there are other boxes that we have that could go on that slide. And one of the great things about having a factory, one of the great things about having an automated way of deploying all of these pieces is that suddenly you start looking for things to add to it. So to give you an example, one of the things that wasn't on the previous slide was quantization. Right? You have a model, let's say it's in bflow 16, but you really want to adjust it down to int4 or FPA or whatever it is. Now, one way to do this is just, at the end of training, I'm just going to manually quantize my checkpoint. Great. But actually, shouldn't we evaluate that earlier? Shouldn't we look at how our models perform post-quantization if we're going to quantize them? Shouldn't we see how that impacts how we do on certain evals, how the performance is, how just various different qualities? And the answer is yes, right? We should do this earlier. And so when you have a factory like this, when you have all of this orchestration, all of this way of actually running things, suddenly you start looking for more things to add to it. And it kind of builds on top of itself. It kind of helps you to get better at building models by virtue of the fact that it exists. As a follow-up point to that, so one of the things that I really glossed over earlier was we have this thing down here. We have code execution platforms. And what this is it's our way of, we take some repository, we containerize it, we make it so that models can interact with it. Now, that process, it turns out, is actually really tough to do statically. It's really tough to do that from some predefined set of rules. With Python, it's probably quite easy, right? You just type pip install and life is good. But if you've got a C++ project, that's really tough. And one of the really frustrating things for me personally was that humans are really good at this. Right, we know, I'm just going to look at the README, I'm just going to follow the instructions, I'm going to type make install, and life is good. But it's much harder to statically teach a machine to do that. But something we really noticed early on was that actually models are really good at this. If you have an agent, it becomes very, very easy to do this. And so what we did was we built a model that could build containers, and then we use those containers that were built to improve subsequent iterations of our model. Right? Because suddenly they have a much wider variety of tasks that they can do when they're training. And you can see how all of this really feeds into itself after a while, right? If we get a good model, we can make better synthetic data, which means we can make better models next time. We get better at evaluating, we get better at annotating. All of these things get better by the virtue of having all of these pieces in place. Now, this has been a really brief summary of everything here. I know I've whizzed through a lot. We have something like 35,000 words of write-up on this on our blog. If you're more interested in any of the details, of course, please feel free to come up to me. But I also recommend that you go and read those if you're interested, because it has way more of the details and rationale behind all of the stuff here that I otherwise wasn't able to get into. And lastly, in closing, I want to talk a little bit about myself. So Poolside really was my first exposure into AI. I didn't come from this. And in a lot of ways, I feel like I have gone from an artisan to an industrial worker. I have gone from making things that were very small, that were very detailed and beautiful, to making something that matters at scale. And if that journey resonates with you, if that's something that you're interested in, then we're hiring. Please come and talk to me afterwards. I would love to hear from you. And with that, oh, there's one more thing I forgot. This is what this looks like in practice, just to be abundantly clear. So I mentioned earlier about filtering. I mentioned earlier about how you take your data sets and you go through them. This is an artist rendition of what that actually looks like. So when you have your data set, when you take it and you go through all of these different steps, this is what it looks like in practice. This, I have to point out, is, like I said, an artist rendition, right? This is not how it actually looks. But this is the main idea. You can see everything in an acyclic graph, and life is all good. And with that, I'd like to end. Thank you all for listening. Happy to take any questions.